Thank you so much for that introduction. And it really is my honor to be here and have a chance to talk to all of you. I want to start off by noting that all the technical content in this talk is joint with many other people, but I particularly want to call out my colleagues, Sylvia Ratnasamy and Jan Stojka. So as the subtitle, I describe myself as an accidental engineer, and I wanted to give you a little bit of background because I think it'll explain where I'm coming from. My father was an experimental physicist. My brother is a theoretical physicist, and I was a theoretical physicist. That's what I got my PhD in. But early in graduate school, I finally realized I was different from the other students. They seemed to care why the sky was blue and the grass was green and why protons were the way they were, and I just didn't care at all. What I liked was solving problems, and physics was just an area where I could solve them, but I found out that I could solve them anywhere, and actually my PhD thesis is on a 6-page paper on the map of a circle onto itself. It has very little to do with physics. So I've wandered from physics to many areas of computer science to economics and game theory and back, all the time just looking for these conceptual problems. And I've often worked on problems that were motivated by reality, but the solutions were not practically relevant. But things like our work on distributed databases when I was at Xerox PARC led to bounds on the optimal way to spread a rumor. And that's not particularly practically relevant, but it was inspired by things. But over time, I've slowly turned into an engineer. And what I mean by that is I now actually care about real world impact, that the ideas, the things that I work on, I actually want to change the world in positive ways, not just as a plausible motivation for my work. And so when you think about achieving real world impact through engineering, we typically assume that this requires technical innovation, that's our job, to invent something new that we couldn't do before. But that's only part of the story, as this audience, which has such a broad set of backgrounds, is much more aware of than I am. But innovation is really only part of the story. So technology ecosystems play a critical role in this. So let's talk about what those ecosystems are. By an ecosystem, I mean a set of economic actors and how they interact. So by the actors, I mean, sort of like in networking, you think of the ISPs, and then their equipment providers and their application providers and so forth. And then how they interact is both the technical interfaces, like the design of the internet, and then there's the flow of money, of how money flows throughout the ecosystem. And the structure of a technology ecosystem dictates how innovations are brought to market, meaning which actors bring them to market. And that in turn dictates which innovations are brought to market, which then dictates the societal outcomes. My first exposure to this was when I was working on packet scheduling algorithms and routers that, by providing isolation and fairness, you actually could get much better outcomes. And I went to the CTO of a major carrier, and I explained why this would make the internet better. And he just said, my customers don't pay for fairness. And I tried to explain how it would make the internet better and everybody would be better off, and so people would pay more. He said, it doesn't matter. My customers won't buy it. So that was my exposure of how an ecosystem defines a set of gatekeepers, and what they care about determines what gets brought to market. And their incentives rarely completely coincide with society's goals. Now, when the gap is small, life's not perfect and we can accept it. But when the gap between what the gatekeepers allow and what society needs, I call this an ecosystem problem. And ecosystem problems are very different from technical problems. So let's compare the two. A technical problem we all know about. If we invent a new way of doing X, then systems would be better, where X is some hard technical problem that you measure through, technical measures of speed or cost and so forth. An ecosystem problem is where if the ecosystem actors did X, it would be much better for society. where X is something they could adopt, but they just haven't for reasons of incentives or lack of coordination or lack of imagination. But notice that here, the difference is they have very different symptoms. One is a technical symptom, the other one is a societal symptom. And they also have very different bottlenecks. One, you have to invent something new, and the other one, you just have to adopt something that may not be technically hard. Now, engineers often ignore ecosystem problems because we're experts in inventing technology, not in achieving adoption. And most of us just treat adoption, that's a business and marketing issue. That's not research. My central point in this talk is that engineers can and should change ecosystems for the betterment of society, for the simple reason that if not us, then who? Who else can change them? So the focus of the talk is on something I'm going to call the technology ecosystem transformations, or TED, as in the Vietnamese Lunar New Year. Think of this as a way of bringing a new era to ecosystems. Now, before explaining what I mean by this technically, we have to face a very unfortunate fact that changing an ecosystem is hard. These ecosystems are huge. Think about the internet ecosystem. There are hundreds of billions of dollars in these companies. They're very large companies, and they occupy very different places in the ecosystem. So changing it is extremely difficult. And so upfront, we have to accept that most of these TED efforts are going to fail. So why should engineers even bother to try changing something so massive? And so that really gets at the goal of what is the goal of engineering research? Now, many of us want our research to have real world impact. Some of us just care about scientific impact, and that's orthogonal. I mean, that's great. But if you want to have real world impact, how do you measure that? And the metric we typically have is adoption. Will this idea be used in practice? Clearly, if it won't be, you've had no real world impact. And if it does get adopted, you have real world impact. So my thesis today is that's absolutely the wrong metric. That's the wrong metric for real world impact for two reasons. One, it only reflects the desires of the ecosystem gatekeepers, because you can only get things adopted that they're willing to adopt. And it completely ignores the impact on society. So a better metric is what I call expected societal impact. That is the probability of adoption times the societal impact of adoption. So you take into account both, will it affect the real world, and how big is that impact on the real world? But even this actually misses some important points. So let's consider these two terms carefully. So when we think about a technical problem, both of these terms are highly uncertain. In terms of societal impact, there's a very weak link between technical metrics like, reducing the flow completion time in a data center and the societal impact. It gets very attenuated when you get outside of the data center. And the probability of adoption, we grossly overestimate this. Take things like congestion control algorithms, for example. There are hundreds of papers published on these every year. How many are deployed? Maybe one, maybe two. We're talking about a probability of adoption that's in the single digits of percents in the best case. So the probability of adoption is much lower than we think, and so is the societal impact. Ecosystem problems have a very different profile. Their societal impact is very significant because otherwise we wouldn't call it an ecosystem problem. The more problematic issue is the probability of adoption. Because didn't we just say that adoption is determined by the gatekeepers and they won't adopt it? So the probability of adoption is zero, no matter how big the societal impact is? Well, the whole point of the TET paradigm is to increase the chances of adoption. That is, I am advocating that we start with societal goals and then we try and get them adopted. We don't start with what will be adopted and let that limit our goals. because that second is what we've been doing so far, at least in the academic arenas that I play in. So the world needs both. So this is not a plea to replace all technical projects with the TET paradigm. We, of course, need to make technical progress. This is merely a plea to add TET to our repertoire of research, because there are some societal goals that are not reachable without trying to change these technology ecosystems. So more generally, what I'm asking us is to look beyond the gatekeepers in setting our goals and imagining our futures. And in doing so, this is not by ignoring deployment issues. For those of you who are familiar with the clean slate research agenda that happened about 20 years ago, there we did ignore deployment issues. Here we're not ignoring them, we're trying to solve them. And that's very different. Now, our group at Berkeley stumbled into this. I co-lead a group with Sylvia Ratnasamy, and then we do a whole bunch of normal technical projects in networking and systems. But Sylvia, I missed it, but Sylvia noticed that our work was shifting to ecosystems, not completely, but some of our work was shifting there. And that was because that's where the barriers were. We would ask ourselves, well, we have this problem, why don't they do X? And we realized it's not because X is hard or impossible, it was because they just chose not to. And so if you wanted to change the ecosystem, you had to change their incentives. So we now have a bunch of ecosystem projects, and all of these were many other collaborators, so I'm not claiming ownership to these. One is trying to create a more cost-effective cellular ecosystem, and that's being led by Sylvia. Trying to preserve and improve the public internet. Trying to create a cloud ecosystem that supports portability. And trying to create an ecosystem that preserves the privacy of photos. And so you can see that these are research agendas that are taking on huge challenges, and many of them are likely to fail. So what I've tried to give you a rationale of why we need to try anyway. But what I haven't given you an idea of what actually technically such a project looks like. So let me take a very simple example. So the privacy of personal photos. So the scenario I'm envisioning is you have, somebody hacks my phone. I've got pictures on it that are embarrassing. They're posted online. I'm powerless to stop their distribution. The incumbents, the Facebooks of the world, they're not motivated to help me. So this is the very definition of an ecosystem problem, that there are things that are bad for society that are happening that are not that technically difficult to solve, but just aren't being solved. Now, the conjecture here is that many users would respect a victim's desire for privacy, but they would have to be aware of it. The user would have to be aware of it, and it would have to be enforced by default by their browser. That is, it's not that you want people to say, here is a really embarrassing photo, do you want to see it? You want the browser to just have a setting that says, don't show you pictures that the owner of the picture doesn't want shared. So if you believe that conjecture, then to leverage this insight, we could deploy a grassroots design. And by grassroots, I mean, this is something not deployed by the Facebooks of the world, but by others. You could design a phone app that signs every photo and then registers it with some back-end registry, whether or not you want it shared. And then some of the privacy-oriented browsers like DuckDuckGo or Brave or Mozilla, they enforce it, meaning when they're going to show a picture, they check for a watermark, and if the watermark is there, then they go and they check whether or not this is shareable. So, our very good grad student designed this and built this system. But how could we possibly think this is going to transform an entire ecosystem, with tens of billions of dollars of revenue? Well, this grassroots approach scales to roughly 100 billion images, just back of the envelope kinds of calculations. That's pretty sizable. That's enough to change consumer expectations and legal liability. Because at this point, the ownership of a picture and the desire for privacy are now cryptographically provable. And so you can imagine if you're a site like Facebook and you show a picture, it causes harm, and it is absolutely obvious if they just checked for a watermark and then checked the registry that they could know that it was being shared without the owner's consent. At least in the US, they're going to be legally liable. And other companies are going to make privacy, their motto, their competitive edge, given this facility. So given this kind of beginning of the ecosystem, the content providers might look at their own incentives and decide to deploy their own internal mechanisms. And once they do it inside their own image processing system, this is trivial to do. It's only hard to do when you have to rely on the browsers to do it. So this is easy to implement at scale. Now, nobody would claim that this solves the privacy problem. If somebody else takes an embarrassing photo of me, we can't do anything about it. We won't be able to prevent these being shared on the dark web. But it's a significant mitigation to the problem. And it's a serious problem that actually, particularly young kids, high school age kids, suicides and extreme anguish happens when these embarrassing pictures come out. And there's not much we can do about it now. And so what's important to recognize here is societal impact does not require scientific completeness. If you looked at this as a security paper, academic paper, it would be shot down because there are many loopholes. But in terms of having an impact on the health of young people and the pictures that are being posted about them, it would definitely have an impact. So why did I go through this particular project? Because it illustrates 5 common themes in this kind of TET paradigm research. First, you have an ecosystem that causes or tolerates a problem. You have an insight that provides hope. You need an insight because you look at the societal problem and you realize the gatekeepers are not taking action. So is there some piece of insight we can leverage to change that? That insight leads to a technical intervention that can be deployed now. And now meaning, A, it's only a modest undertaking. It's not a multi-year project. And B, it doesn't involve the incumbents. You're not asking Facebook to change right out of the gate. But the point of this intervention is that when it is deployed, it changes the incentives for the incumbents. And those incentives are enough so you just let market forces and self-interest do the rest. Because remember, you're not trying to depose the incumbents, you're just trying to change them to act in a more societally appropriate way. So those are the 5 themes: a problem, an insight, an intervention, whose deployment then changes the incentives. Now, you can ask the question, is the TET paradigm research? No, because TET doesn't necessarily require you to invent novel or clever technology. So most people don't consider it research. But TET does require solving a hard design problem. It's hard because you must identify the right technical intervention. It's got to be deployable, and that means deployable not by the incumbents. It's got to be commercially viable. You're not expecting people to do this out of the goodness of their heart. And it's got to change the incumbent incentives. So designing an intervention that satisfies all 3 criteria is hard, but it's not what academics normally do. Because as Don Norman famously said, academics get paid for being clever, not for being right. But I view that that's a problem with the academic ecosystem, not with TET. I definitely consider TET to be research, and that's something we'll have to get back to later in the talk. Now, as this audience is obviously aware, this combines many strains of related work. There's engineering of practical and scalable systems, because these are really deployed systems, they're not paper designed. It involves disruptive innovations, the crossing the chasm kinds of thinking of how do you insert something into an ecosystem. But what's different here is you're not trying to depose the incumbents, you're just trying to change their behavior. So you have to think about this as a mechanism design in terms of game theory. And then there are a lot of legal and policy considerations because often the incentives come about because of legal or policy ramifications. So there's lots of related work, and we're just putting it together in a way that at least I haven't seen before. So the rest of the talk, I want to describe two additional examples: transforming the cloud computing ecosystem, something we call sky computing, and transforming the internet ecosystem, something we call interedge. Now, the technical discussion is going to be vastly oversimplified because my focus is in how they exemplify the TET paradigm, not on the technical details of actually how they work. So for each of them, I'm going to cover some basic context. I'll describe the societal problem. I'll describe the insight and intervention, and then I'll describe the impact of the intervention in terms of incentives. And I'm going to end with some comments about the academic ecosystem. Okay, so let's go to the first example, which is cloud computing. Now, the context you all know, clouds offer both infrastructure in terms of various instances of VMs and services, things like data analytic frameworks or message queues. And these service offerings are typically proprietary. And if you use them, they're designed to be used because they make your life better. If you use them, it's difficult to shift workloads to a different cloud, producing lock-in. And that causes a societal problem because this lack of portability leads to a very concentrated market. You know, the two largest clouds have greater than 60% of the market share, and nobody else has more than 10%. It's very difficult to satisfy sovereignty and resilience requirements because you're locked into a single cloud. And if they go down, you go down. And you can't use best-of-breed hardware and software. That is, if somebody comes up with a better solution to part of what you're doing, you can't utilize their solution. You're stuck in the cloud that you're in. But the key insight here that might relieve the societal problem is that many of the cloud compute tasks can use open source tools, which can run anywhere. So let's leverage those tools to make jobs more portable. Okay, so what's the intervention for cloud computing? The intervention is to create third-party, what we call intercloud brokers. A user submits a job description to a broker. That job description describes the computational requirements, instances, and/or services, and describes the criteria for placement. Do you care about cost? Do you care about performance? Do you care about location? And the broker then places the job in the appropriate cloud and oversees its execution. Now, this description is vastly oversimplified, but rest assured, we have built a prototype. It's in active use by people who are using it seriously, to get their computation done. So that there are many hard problems here, but I'm just brushing them under the rug. Now, what's the impact of this intervention? Well, it creates a fine-grained, two-sided market. It's fine-grained in that it's sort of per computational task. You're not deciding on your whole workload all at once, but for each task, you describe it, and the users are on the one side, they describe the task that they want, and on the other side, you have the clouds who have these services that you can utilize, and brokers find the best match. And if your task involves like a pipeline of computation, you can split the job across multiple clouds, leveraging the best of breed of everything you want to do. Now, it's important to note the clouds don't have to opt into this market. They don't have to say, oh, we want to participate. The brokers can just leverage the kinds of services the clouds already publicly offer. And then the resulting competition will hopefully cause the clouds to change their behavior. Now, some of them are going to stick to proprietary services because that's how they've made their money, but others are going to focus on open source and other widely supported non-proprietary services. They'll do that because people who are looking for the cheapest price will want to use services that are available across a wide variety of clouds. And it'll make it easier for specialized clouds to emerge. You don't have to advertise. You don't have to make sure people know. If you have a cheaper GPUs, the brokers will find you and bring you customers. So the important thing to recognize here is you change the nature of the competition. It used to be if you started a new cloud, customers will say, do I want to start with this new cloud, which is small and underdeveloped, or go with one of the big clouds that has a huge range of services I can leverage? And the huge clouds are typically winning. That's why we have a concentrated market. Here, because the brokers are this intermediary, the clouds that remain focused on proprietary services have to compete against the union of the other clouds. And that's a much fairer fight. So the resulting cloud ecosystem is something we call sky computing, because it creates this declarative job interface to the sky of computing. You don't pick your individual cloud. You just describe what you need, hand it to a broker, and they pick out which cloud that you can use. It makes it much easier to optimize for a variety of criteria, so users are happier. And the resulting portability, and therefore the competition, leads to more innovation, better performance, and lower prices, and a huge societal payoff. So that's the cloud story. And again, we know this is oversimplified, but we actually have a real system that's working. The second example is about the internet. And the context here is, when we go back to the public internet, and I call that the original internet is public because it was sort of an open service that anybody could pay for. It's simple, just supports best effort. It's interconnected in that the ISPs cooperate to provide end-to-end delivery. It goes from an access ISP to a transit ISP, maybe to another transit ISP, and then to the other access ISP. And it's neutral. It's a level playing field for applications to innovate. Now, the current internet is different. It has many in-network enhancements. There's caching, as in CDNs, that are all over the place. There's DOS protection, there's load balancing, there's zero trust, there's next generation firewalls. And these aren't implemented in routers. They're implemented at the network edge on these general purpose compute clusters. Now, what's important is these edge enhancements do not interconnect. That is, two CDNs don't peer. They don't know how to hand off traffic to each other. And what that means is that global coverage now requires global infrastructures. That's very different than the interconnected ISPs of the classic public internet. Here, global coverage requires global infrastructures. And so to deploy their enhancements, the hyperscalers have built these large private networks. And these large private networks are starting to replace the public internet. And the amount of transit traffic is much less than it used to. The fraction is, somewhere, between 30 and 20% of the traffic actually does not use a transit ISP. Now, why is this a societal problem? Particularly, this question is relevant because today's internet has much better performance. So these enhancements have actually helped in terms of the quality of service people get. But this trend transforms the internet from a neutral platform into a set of parallel and customized networks that only provide delivery to and from their own back-end data centers, are inherently tied to providers of application services. This is not simple, it's not interconnected, and it's not neutral. Now, some of my colleagues disagree with me, but for me, if we value the internet as a ubiquitous and neutral enabler of innovation, this is an unacceptable outcome. Societally, this is unacceptable. So the insight here is the key challenge is to interconnect the enhancements. It's the lack of interconnection that meant that we had to have these new global infrastructures. And I mean interconnect as in the original internet, that is you want these enhancement providers to cooperate in delivering the appropriate edge services. And so this would create what we call the interedge. Just like the internet connected a bunch of networks in an interconnected way, here we're trying to do the same thing for these edge services. So this is our intervention. So the interedge must, one, provide standardized set of enhancements, because you can't interconnect if you don't agree on what the service you're providing. And you want it to be evolvable because these edge services, we've been adding them over time. And it's got to have a feasible economic model, which actually turns out to be a hard problem. But we have such a design. We're building a prototype that we're going to open up in a couple of months for broad usage. But the key question is who's going to deploy and who's going to use the internet, InterEdge. And we think they're two symbiotic components of the ecosystem. In terms of potential users, we think smaller clouds and content providers, right now they've got to compete with the enhancement used by the hyperscalers. The hyperscalers have spent a tremendous amount of money building out these private networks, so they must be getting something in return, and it's hard for the smaller clouds and content providers to compete. But they can't afford to build their own large private networks, and they don't want to be locked in to a single enhancement provider. In terms of potential deployers, you have the independent enhancement providers, sort of CDNs. They need customers, but they want lower barriers to entry. That is, you would like it so if East LA or some other part, of the world isn't being adequately served, that you could have an enhancement provider that goes into that part and serves them, and it can interconnect with the rest of the enhancement providers. InterEdge offers a solution to both of these needs. It's a standardized set of enhancements with many potentially local providers. So what's the impact of this intervention? The large network providers, they're still going to keep their networks, but they'll be competing against the union of all these InterEdge providers, much like what happened in the cloud. And these private networks will then have an incentive to adopt the InterEdge enhancements. They'll have that incentive because the application providers want to avoid lock-in, so they would prefer to go with enhancements that are common across many providers. But it also allows them to easily extend the reach of their own networks. If there are places of the world they don't cover, they can use one of the current other providers to do that. And, we've talked to people, their enhancements aren't very specialized. There's really nothing proprietary or special. They've just built their own code, but it's not like there's secret sauce there. So adding the InterEdge to the internet would restore neutrality and interconnection, would increase evolvability because you can add these new enhancements. And the societal payoff is an enhanced and evolvable public internet. This is something many of us who care about the internet have been trying for decades. Okay, so that's the two examples. So, we can talk about later in the Q&A, but I really just wanted to use them as examples of the TET paradigm. Let's return to TET as a paradigm. We can't know in advance if a TET project will succeed, and we know the odds are low. But we'll never know until we try, and we aren't trying now. So what are the incentives for trying? So for the incentives for companies are actually these ecosystem projects are often quite modest in scope compared to deploying global infrastructure, but they may significantly alter the competitive landscape, changes that would be very hard to bring about more directly. That is, if you're a cloud that's starting out, you don't want to compete directly with the Amazon and Azures of the world. Instead, if you know you can't beat them at their game, what you want to do is change the game. And that's what TET offers, is a way of changing the game. So, if you take the combination of Sky Computing and InterEdge, they could give other companies that are not dominant now, that are not hyperscalers now, a central role in the modern cloud and internet. You could become an intercloud broker without global infrastructure. You can become a supplier of open source software for the InterEdge without having global infrastructure. That it opens up the market in ways that you couldn't do with head-on competition. For individuals, the reward of doing societal impactful work is great, but professionally, the rewards are very small. Academia focuses mostly on cleverness, as Don Norman's quote, and/or success. You're not rewarded for failure. So how can we change academia to accept this as a paradigm? So that brings up the problem of, we're in the business of fixing ecosystems. So how do we fix the academic engineering ecosystem? And I think it's really just promote the notion that ecosystem change is possible and that we as a community should pursue these agendas. But we often encounter these vehemently cynical reactions. This will definitely fail. This isn't research. This is not worth publishing. It's really interesting how vehement they are in these objections. And I think the community instead should focus on the slim hope of success. And it's really important here. By hope, I don't mean deluding yourself to think that you are likely going to succeed. It's just saying, yeah, I know it's a 1% chance, but I'm going to do it anyway, because a 1% chance of changing the internet for the better, I'd take that any day of the week. To me, the central question for those who object to this is, how else can we address these ecosystem problems? What else do you suggest? Or are you just going to accept the problems that we have? And it's important to note that some other fields do focus on these high-risk goals. If you look at medicine, sure, big pharma, focuses on things like curing bunions just because that's something people will pay for, it's low risk. But if you look at academic medical research, they try and cure incurable disease. They actually take on things knowing that chances of success are very low. How many people work on curing cancer? How long have we been after that? But that's what people accept, that it's much more important to go after these high-risk goals because of how important they are. And our community used to believe that too. I mean, how did the internet come about? So this is the intervention the academic system needs. So I'm going to now end with a simple summary of a very complicated story. So I know I've oversimplified it, but if we as technology innovators want to change the world, then we should consider working on ecosystem problems. The initial cost is relatively small compared to deploying global infrastructures. It can have a huge impact on society. It can have a huge impact on companies. And it can have a huge impact on individuals. But the community must decide to embrace this challenge. And that means not settling for easy successes. We have to be willing to endure if we're doing it personally, or encourage, just as part of the community, these valiant failures. And with that, thank you for listening, and I welcome your questions.